You know, when you see a massive oil refinery or some sprawling chemical plant, you see this incredible maze of pipes and towers and tanks. But what you don't see is the invisible layer of engineering. It's this meticulously designed blueprint that keeps these incredibly powerful facilities from, well, becoming catastrophic failures. Today, we're going to pull back the curtain on that very blueprint.
So let's just get right to the heart of it. What really stops one of these industrial giants from exploding? I can tell you, it's not luck. It is a carefully, meticulously designed system. It's like a constant conversation between physics and chemistry and engineering, all working together to answer that one single question every single second of every single day.
And the main threat, the number one thing this whole system is built to fight, you could call it the villain of our story, is a phenomenon called overpressure.
So what is it? Well, simply put, overpressure is what happens when a container, any container, gets hit with more pressure than it was built to handle. The best analogy is a balloon, right? You keep blowing, the pressure builds up, and then pop. Now just imagine that balloon is a 10-story steel tower filled with flammable stuff. The consequences are, a little more serious.
And look, this isn't just some abstract theory. The engineering standard we're digging into today, API 521, it describes these worst-case scenarios with, honestly, some chilling detail. It talks about things like a superheat limit explosion. That's where a cold, volatile liquid suddenly hits something much hotter. It can flash into vapor almost instantly, expanding with the force of a detonation. We're talking about an event that happens in microseconds, creating shock waves, just an insane release of energy.
And that's the absolute key right there. For an event that violent and that fast, a standard safety valve is totally useless. It just can't open fast enough. And this really highlights a core principle of industrial safety. The best defense is making sure these scenarios never, ever happen to begin with.
Okay, so how does a plant even get into one of these dangerous situations? Well, it's not just one thing. Engineers have to look at the anatomy of every potential upset condition that could possibly happen.
And when you look at the common causes, you see just how diverse these threats are. You could have a huge power failure that knocks out the pumps circulating cooling water, and then temperatures and pressures just spiral out of control. Or it could be simple human error, like closing the wrong valve and blocking a critical exit path. An external fire can literally boil the contents of a tank from the outside. And get this, even something as gentle as the sun can heat a trapped section of pipe and cause the liquid inside to expand with enough force to rupture solid steel.
Now, with all these potential causes, you're probably thinking, wait, do they have to design for everything happening all at once? And the answer, thankfully, is no. That would be just about impossible. Instead, engineers rely on this fundamental design principle called single jeopardy. The whole idea is that the safety system has to be robust enough to handle any single, credible failure.
And this example really makes it clear. Designing for an external fire, that's a single jeopardy event. It's a credible risk, it could happen. But designing for a fire that starts at the exact same microsecond that a totally unrelated pipe ruptures somewhere else in the plant, that's double jeopardy. It's considered so ridiculously improbable that you don't design for it. This principle is what keeps engineers focused on solving realistic problems.
Okay, so if we can't prevent every single overpressure event from starting, how do we handle them safely when they do? Well, this brings us to the hero of our story, the pressure relief and disposal system.
Let's actually trace the journey of all that dangerous excess pressure. So an upset starts, and a pressure relief device, a PRD, automatically pops open. That directs all that high-pressure stuff into a special network of pipes called the flare header. But before it can be burned, any liquids have to be removed in a big vessel called a knockout drum. And then, finally, the clean gas flows up to the flare tip where it's safely burned off.
Let's zoom in on that knockout drum for a second, because it's such a critical safety barrier. It's basically just a giant empty tank. As the high-speed mix of gas and liquid rushes in, the space suddenly gets way bigger. That causes the velocity to just plummet. And when it slows down, the heavier liquid droplets just fall out of the gas stream because of gravity, collecting at the bottom. It's simple, but it's brilliant.
So why is that so important? Well, because the absolute last thing you ever want is a geyser of flammable liquid shooting out the top of a 300-foot flare stack. There's a name for that. It's called flaming rain, and it's as bad as it sounds. The knockout drum is the number one thing that makes sure that never, ever happens. So you see, the flare system is so much more than just a pipe with a flame on top. I mean, yeah, its main job is to safely burn off gases,
especially those huge surges you get during an emergency. But it also has to stop the flame from traveling backward, that's called a flashback, into the plant piping. And it has to stop air from getting sucked into the header, which could create a seriously explosive mixture. It's a really dynamic, multi-talented safety system.
So where do all these rules and designs come from? I mean, who decides how big a knockout drum has to be, or how strong a pipe needs to be? That brings us to the bigger picture, the implication, the blueprint itself.
This whole system of defense, from figuring out what can go wrong to designing the flare at the very end, it's not improvised. None of this is guesswork. It is all based on a really comprehensive document, a global standard from the American Petroleum Institute called API 521. This is the rulebook. And this is what that engineering looks like in the real world. Now don't let this chart scare you. You don't need to know what a latent heat of vaporization is. The point is to see that engineers are not guessing. They're using complex charts and performing rigorous calculations like this one to figure out exactly how much vapor is going to be generated in a fire, and because of that, exactly how big the relief valve and the piping needs to be. Every single decision is backed by data and physics. And this isn't just for one little type of plant. The principles in API 521, they're the bedrock of safety design in oil refineries, petrochemical plants, natural gas facilities, LNG terminals, all over the entire world. It creates a common language, a common standard of safety for the whole industry.
So really, the big takeaway here is that our modern, high-tech world is literally built on a foundation of these invisible rulebooks. Standards like API 521 are the collective knowledge and sometimes the hard-won tragic lessons of generations of engineers. It's all written down to make sure these incredibly powerful processes can run safely, day in and day out.
And it really makes you wonder, doesn't it? From the electrical code that keeps your house from burning down to the standards that govern air traffic control, what other invisible rulebooks are out there, quietly and thanklessly, just keeping our complex world from falling apart? It's definitely something to think about.